So hi everyone, my name is Paul. I've been doing machine learning since 2009. I was fiddling around with neural networks and reinforcement learning back then for my honors thesis for my electrical engineering degree. So you can find me on Twitter here or LinkedIn. I like to tweet about all things machine learning related. And yeah, I think actually Twitter is a pretty good platform for finding out about the latest and greatest in machine learning. So as Tim mentioned, I'm the founder of Sydney Machine Learning. We are the largest group of practicing machine learning practitioners in Sydney. And I'm also the founder of Star AI, which I'll talk to you about a little bit right now. So through my work in this field, I've been lucky enough to meet a lot of different people in the machine learning space, and I've found three intersecting problems that work together quite well to achieve essentially the top thing. So I've run a lot of courses, like educational courses, and through that I've found that I know that there's a lot of like professionals right now, be it like developers or graduates coming out of university that are trying to transition into the machine learning field. But there's this problem called the cold start problem. And what it is getting your first foot in the door, essentially. So once you got your foot in the door, once you got your first job, then your career is set up and you can go for gold, but getting that first job is really hard. The second side of this, the second circle on the left, companies that are trying to apply machine learning, is the second problem. So there's essentially two parts that make that part up. The first part is that extreme machine learning talent right now is expensive. It's very expensive. So a lot of emerging machine learning companies find it hard to hire these people because they're expensive. The second part is that there's not really a lot of them. So through my work in studying machine learning and teaching all these courses, I've come to find that there's a lot of people that want to transition that have really high skill sets, but they just can't land that first job. And I think that there's a good match here between emerging ML companies and professionals that want to transition into machine learning. And finally, the last part is research. So I myself am kind of faced with this problem, and I meet a lot of people that are faced with it too. And that is, when you get to a certain level in Sydney, there's pretty much nowhere to go. You have to go to either have to go to San Francisco. I mean, there's CSIRO, there's the universities that you can go to. There's a handful of high-tech startups that you can go to. But apart from that, once you reach a certain level, you pretty much have to go to San Francisco. So I myself have been working really hard on the top one. And so I'm now heading up Star AI. And what it is, so Star AI Applied Research, and what it is if you are a machine learning engineer as a data scientist, the general goal is that we're going to send you out as a consultant for 4 days, 3 to 4 days where you get to work in an emerging ML company. And then on the fifth day, you pitch us a machine learning project, be it whatever it is, say, doing work with GANs or whatever, and get to work on your research idea. This is kind of how like Google has that 1 day off a week where they get to do whatever they want. In this case, the whatever you want is your research idea, and that one's on us. So yeah, if you are a machine learning company that needs talent, or if you are an emerging ML company, we'd love to hear from you. And feel free to contact me at that address, contact@starai.io. All right, so this is the format of today's talk. I'm pretty excited to be giving it to you guys. The first part, we're going to briefly talk about why we're even talking about machine learning in 2018. The second part is the main focus of today's talk, which is what machine learning is capable of in 2018. And then we're going to run through some basic ML algorithms. Feel free to take pictures of the slides, because if you want to get into this, there's some resources which you can pretty much follow up after this talk, and that should lead you on to being able to implement machine learning yourself. All right, so today I'm going to introduce 3 fundamental key concepts that machine learning can do in 2018. And then we need to introduce those before we jump into explaining a couple of algorithms and how they work, okay? So that is what today is going to be all about. So what can machine learning do in 2018? So the first idea is classification, and a lot of this stuff is trivial to a lot. Well, it'll seem trivial to a lot of you, but we're building these ideas, and we're going to sort of like layer this on like a cake, so you can understand the later concepts. So the first one is classification. It's pretty straightforward. It's the idea of like, say you've just washed the dishes, and you've got a whole bunch of knives and forks. You take the knife, you look at it, you say, okay, that's going in the knife bucket. Got a fork, that's going in the fork bucket. Got a spoon, and so on and so forth. So this is kind of similar with machine learning. Say you're analyzing a whole bunch of customers and you're looking for fraudulent behavior. What you do is you take your customers, you run it through some machine learning, and you put the fraudulent customers in the fraudulent customers bucket, and then all the customers in the other, like the good customers bucket. So that's classification in a nutshell. And there was this famous use case in 2016, I believe, where a Japanese farmer, traditionally he had to hire people to sort cucumbers, to look to see whether like it was a good cucumber, there's nothing wrong with it or whatever. But what he did is he went and he used machine vision and essentially did classification. So he looked at the cucumber from different angles and was like, okay, this is a good cucumber, we'll keep it. And in this example, you can literally see it's going in a bin, like we're talking about with classification. It's going in the good bucket, which is the one on the right. One on the left, it goes to the bin. Right, so that's classification. The next one's prediction. Again, very trivial. Prediction is essentially just predicting some number in the future. So, for example, say the weather. We've been doing this for almost 100 years, trying to predict, based on a whole bunch of data, predict some kind of future outcome. That's prediction in a nutshell. So like a classic one is just predicting stock market shares. So say, for example, you've trained a model on Tesla's stocks, which is quite volatile at the moment. You can use machine learning to kind of do prediction of some kind of metric in the future. And the third one, which is the topic which I myself am most excited about, is control. So you can do control with machine learning in 2018, and there's various ways of going about this. But like one of the most famous use cases is Google's data centers. So they acquired DeepMind, I believe, in 2015. DeepMind is a machine learning research company, for those who do not know. And they applied DeepMind's machine learning technology to Google's data centers. And they were to get across the significance of this, these data centers are already highly optimized. So they've already hired a whole bunch of engineers to come along and make sure it's all running really efficiently. They applied the machine learning technology on top of what was already there, and were able to save 40% in power reduction used by the data centers. So just by itself, just by that number, DeepMind was able to essentially pay for itself. So those are the 3 things. We talked about classification. You can do classification in 2018. You can do prediction. And you can do control. There's a whole bunch of other sort of minor ones, but those are the 3 majors. All right, so we sort of set the stage now by talking about what machine learning can do. Let's now talk a bit about the different types of machine learning that exist. So there are essentially 3 major flavors of machine learning. There are supervised learning, and we're going to be spending the most time this talk on supervised learning, and you'll see why in a couple of minutes. The next one is unsupervised learning, and the final one, reinforcement learning. All right. So, supervised learning. So, if you are looking to transition into machine learning right now, I suggest you spend most of your time on supervised learning. The reason being is this is where the money is at 2018, okay? That's the reason you should learn about supervised learning. So, what is supervised learning? let's say you have a data set of images and the associated labels that go with those images. So we have an image of yours truly, another image, and the associated label that goes with that image, and another image. So the way supervised learning works is you have your input data sets and the labels that are associated with that input data. You pass your input data into the machine learning model. It then produces either a prediction or a classification on the other side. You measure the error between your label, yes or no, Paul or not Paul, and then push that error back into your machine learning model, and that updates it and makes it a slightly better predictor or classifier. So what you're essentially doing with supervised learning is mapping your input data to the labels. That's essentially what you're doing. You're creating a map between your input data and your labels. Right, so here's a little concept. I'm just going to quickly go through this. You need to bookmark this in your mind for the rest of this to make sense. All right, so in machine learning, if we have a data set, and say in this example we are trying to predict house prices, and we have some data here. If you have a table in machine learning, we call features the columns going right. So all the columns going right here are features, so number of windows, number of bedrooms, size. You could have more, for example, if it has a pool or not, if it's a high crime area, etc. And the next thing, so we call, as you go down, your rows are what we call observations. So here we have 4 houses. There's a little typo there. But yeah, let's say you have 1,000 houses in your data set. There'd be 1,000 different rows, 1,000 different observations in your data set. All right, okay, so there are many different heuristics that data scientists and machine learning engineers use to, when we decide which model we're going to use to apply to a data set. There's quite a few, but the main one is the size of the data set, okay? So based on the size of the data set, it's usually the main heuristic we use to decide which machine learning model we're going to be applying to a specific problem or whatever. So over here, we got prediction and classification, 2 of the tasks we talked about earlier. And in the middle, we have a column of number of observations. That's what that's saying. So that's the size of your data set. So let's say we had between 1 and 1,000 different data points, different rows in our data set. If we were going to be doing prediction, a good model to use is linear regression. This is quite an old one. It goes back to like the early 1900s. But it is solid for data between 1 to 1,000 observations. And it kind of works as follows. I'm not going to go into the very specific details of how this works, but just from a very high level, because we only have a limited amount of time in this talk, is linear regression kind of works like this. You have a data set, and you're trying to fit a straight line to approximate the data set, to try and make some kind of approximation of it. Once you have fitted your model, as we like to say, you can then make predictions on it about data you don't know about. So let's say, for example, in this case, I have been trying to study for a test in machine learning, and I want to know if I study for 67 hours, how well am I going to perform on the test? I can read up the line, read off my model, and know that I'll get 98% if I study for 67 hours. So that's linear regression in a nutshell. Same thing. So that was for prediction. For classification, you know, when the whole buckets thing, where you like picture of Paul, picture of not Paul. If you've got between 1 and 1,000 observations in your data set, a really good model to be thinking about here is logistic regression. This is a tried and tested model. It kind of looks like this. So let's say you are trying to predict whether there's like cats or dogs. There's 2 classes there, cats or dogs. All logistic regression does is it's sort of fitting a boundary between one class and another class. So we could have like cats on the left and dogs on the right. And the beautiful thing about logistic regression is it works. We talked about those columns earlier, the number of features, like number of windows, number of pools in for your house. Logistic regression works like in dimensions. It's pretty good. All right, so we've talked about 1 to 1,000. Now let's if we push the amount of observations, the amount of rows in our data set, between 1 to 100,000, from 1,000 to 100,000, what sort of models can we use there? So this guy, decision trees, is a sort of a staple of the data science world. And the reason being is that you can use it for prediction or classification, and it has this really beautiful property that it is something which is known as interpretable. Now, what does that mean? So interpretability is a big issue in machine learning, and what it means is, say for example, I created a model that I was going to use to predict whether I'm going to hire somebody or not. I'd like to know, I'd like to be able to open up the model and see how it's making its decisions, okay? And one way to do that is use this model, which is called a decision tree. So we train our model, and we open it up, and we can kind of see it's essentially a set of flows, is my potential candidate a certain age? Do they go to a certain, what's their education level, etc.? Yes, no, yes, no. So that's decision trees in a nutshell. This guy, random forest, is essentially the bread and butter algorithm of the data science world at the moment. And the reason being is it's a sort of it's a derivative of decision trees, and it can do prediction or classification, like we talked about at the start of this lecture or talk. And it's a derivative of decision trees. And how it essentially works is a very high level overview. You train multiple decision tree models, okay? And you tweak the parameters of each decision tree model just slightly. And then what you do is you take the aggregation of the output of all the different decision trees, aka a forest, and you take the average of that, and that average is your prediction or classification. So that's kind of how random forests work. And that, again, is the bread and butter algorithm. So if you want to get into machine learning, I suggest you learn that guy. Also, as a side caveat, there's a lot of talk at the moment about big data and all that jazz. Most companies that are trying to get into machine learning right now, their data sets are in the size range, between 1,000 to 100,000 observations in their data sets. There's a lot of companies out there, and that number is going to increase over time, obviously, but right now, that is roughly the numbers of observations that most people have in their data sets. Okay. Now we're going to move to sort of the high-level algorithms. So if you have 100,000 plus observations in your data set, pretty much the main algorithm that's used in production is something that's known as XGBoost, okay? Now, I'm not going to dive into this, but XGBoost essentially borrows sort of the best ideas from random forests and the best ideas from something called gradient boosting and combines them together and gives you the best of both worlds. And this algorithm is implemented in big data set things like Hadoop and Spark, so you can make use of it there. And some examples of companies that are using this are like big banks who have massive data sets, airplane companies, they'll have lots of data they can process, so those sorts of companies. And finally, we get to deep learning. So there's been a lot of hype around deep learning in the last 2 years. Unfortunately, actually, deep learning has not been used very, very much in Sydney at the moment. There are very few people that are actively using deep learning. Multiple reasons for this, mainly because I'd say Sydney is a little bit behind, but also being that it's not exactly the most easiest algorithm to just get going off the get-go, okay? Deep learning is a little bit more complicated. So deep learning, you must have heard, is roughly inspired by how the human mind works. And it's got some really beautiful features, though, that I really wish that this model was being used more in Sydney, because it can essentially infinitely scale. So you can feed it as much data as you want, and it just becomes more and more accurate. That's essentially one of the great positives of deep learning. Okay, so right now on the screen, you have a whole bunch of algorithms that you can take a photo of and start learning after this session. There's a really great library that's implemented in Python called scikit-learn. I suggest you go take a look at that after this. that'd be like the first port of call if I was going to be learning machine learning in 2018. It's quite easy. All right, so we talked about supervised learning. That's the bread and butter side of machine learning right now. I'm going to quickly dive through the other two. So we have unsupervised learning. So unsupervised learning is essentially when you have your data, like your data set of images like we had before, but you have no labels for those images, okay? And what you're trying to do is automatically generate the labels for the data. So in the most commonly used one as a data scientist, this is pretty much the only one you need to know, is one called k-means clustering. And what it is you essentially say, okay, I've got this massive data set. I want to group my data into 5 different categories, for example. And the algorithm will automatically run through the data and make groups of 5, because you said I want 5 groups. And what's going on there is you're essentially assigning the label of the group to the data. That's essentially unsupervised learning in a nutshell. So the best way to understand it is just to see it. So here we're running it on 5 groups. And you can kind of see in this image that the label now is the group that the data belongs to. Like the label of will be from the group is being attached to the data, in a nutshell, is what's going on there. Okay, so that's kind of what you need to know as a data scientist. I'm going to now go through so that's the data science money side of things. We're now going to go through like the cutting edge stuff, the stuff that's emerging on the horizon, okay? Spend some time on that. Right, so there's a famous machine learning researcher called Yann LeCun, and he says that unsupervised learning, which we talked a bit about just before we gave you all those algorithms, that's the icing on the cake, okay? Where the really big progress is going to be is in unsupervised learning, which he represents in this diagram as literally the cake. And unfortunately, we actually haven't made much progress at the moment in unsupervised learning. I mean, k-means, which I showed you before, is actually trivial. But there is something I want to show you where we have made progress, and that's artwork generation. So this is going to be huge probably in the next 12 years, is sort of generating artwork, whether that's speech, like people's voices, actual pieces of art, textures for games, characters themselves, etc., etc. So, picture of yours truly. So let's say, for example, I wanted to paint myself using Vincent van Gogh's sort of style. What I can do is I can apply this technique called general adversarial networks. I ran this on the weekend, and yeah, you get something that looks pretty similar to a piece of art that would have been created by Vincent van Gogh. And this sort of level of technology it's here and now, and it's only getting better. So artwork generation is something machine learning can do right now. Another example is this. This was a piece of research from last year. Guys applied the same techniques to transform a horse to a zebra. And you can see that there's like some errors there. But like I said, like this year we've actually taken this technology even further. So yeah. So that's unsupervised learning in a nutshell. Now when I get to reinforcement learning, this is where I got started in machine learning way back in 2009. And I'd just like to share with you a little bit about this, and then we'll wrap it up. So what is reinforcement learning? The best analogy is kind of like how you'd go about training your dog to give you the paw. So what you do is you put your hand out, you take the dog's paw and you put it in your hand, and you give it a treat. And you repeat this process, you do it over and over. You put your hand out, you take the dog's paw, put it in your hand, and give it a treat. And over time, the dog's brain begins to associate, I'm going to get a reward when the master is putting out his hand. So that's essentially reinforcement learning in a nutshell. We train our models and we assign them like reward labels, either positive reward for something that we'd like them to do, or negative reward to discourage things that we wouldn't want them to do, okay? And this is the technology that powered DeepMind's system that beat Lee Sedol, the Roger Federer of the Go world. Go is a Chinese board game. And this is the technology that powered that. So I'd like to just show you a couple of examples of other things. But first, so state-of-the-art RL, if you would like to know a little bit about this yourself, there's three major ones. There's proximal policy optimization. That's an algorithm that was invented by OpenAI and has recently had much success. I don't know if you have seen it in like the Dota. There was a lot of publicity around Dota this year. That was proximal policy optimization at work. Rainbow, that's an algorithm by DeepQN. And Impala, that's another algorithm from DeepMind. So if you want to get state-of-the-art RL, those are the three you need to know about. And I just want to show you some use cases. So on the left here, we have an example that's from 2008, where reinforcement learning was being applied to a little model helicopter running on petrol, because we didn't have electric drones at the time. So Stanford University was just using a little petrol helicopter here. And they trained it to do little aerobatical maneuvers. And this is using reinforcement learning. So again, it's all about essentially controlling things, making decisions. And they got the little like thing to do some really crazy maneuvers. Like over here, you can see it do stationary rolls, flies upside down. It like imitates like a clock. And that's all autonomously using reinforcement learning. And this here is the latest success from this year. It was actually just a couple of months ago. So OpenAI trained a hand using proximal policy optimization, which is that algorithm I just talked about.
We're working on teaching robots to solve a wide variety of...
To face, so what they wanted to do was face the objective is in the bottom right-hand corner there. So like, let's face E to the camera. And the crazy thing about watching that video there is it almost looks like a human hand, how you would manipulate a block to do the same task. So say you wanted to face O towards the camera, you could see yourself doing the same thing. And finally, this guy. So some of you may have seen it, the machine learning guys may have seen this already, but for those of you who haven't, back in, this is a success from 2015. DeepMind trained one of their reinforcement learning algorithms to play the game of Atari. And right at the start, you can see it's not behaving very intelligently. It's just sort of missing the ball. After 200 training episodes, it starts to play it a bit like how you would imagine a computer to. It's like very sporadic. It's not flowing. After 400 training episodes, it's starting to play a lot like a human would. So like it goes to match the trajectory of the ball. But the real magic happens around the 600 episode mark. So around the 600 episode mark, the algorithm figures out the best way of playing the game. And the way to do that, if you want to know, is you build a tunnel on the side. And then what it does is it bounces the ball around the top and maximizes the score. And this is all autonomously. It figured it out itself. So that to me is pretty crazy. So if you want to know more about reinforcement learning, I suggest you go and check out a library called OpenAI Baselines. You can get it at this address, which is currently on the screen. This is the stable version of it, which is a fork. But the people here have gone to the effort of like commenting the code, making the variable names interpretable so you actually know what's going on, etc. So yeah, that's it from me. I hope you got something out of that, and thank you.